So one of the most important things that we're going to learn in E&M has to do with symmetry. We're going to be looking at these different vector fields that are going on, and we're going to try to use some physics knowledge to knock out some of the really highly intensive math. In these series of videos, you're going to see how nasty the math would be, and then I'm going to try to put in some symmetry ideas, some basic physics ideas to knock down that amount of math. We're going to start with the importance of symmetry in E&M. Let's consider that we have a plastic rod of charge negative Q, so the total charge on this thin rod is negative Q, and that rod lies in such a way that in a coordinate system it makes an angle of 60 degrees, the tip of the rod makes an angle of 60 degrees with the horizontal, and it makes another angle of 60 degrees down here below, and we're at a distance r away. Now the key here is we want to find the total electric field at the origin in terms of Q and R. So find E at the origin in terms of Q and R. Now if we think about this logically, it's actually going to cut down on a huge amount of our work. So let's take a look. If we go back to our coordinate system, and here we have our thin rod. Our electric field, because this is a negative rod, a negatively charged rod, the electric field is going to be radiating upward like that on the two ends and downward like this down here. So this is what the electric field looks like in both cases, the electric field moving towards the negatively charged rod. Now because both of these angles are 60 degrees, that's actually made life super easy on us, if we think about this in terms of vectors. This E has an X and a Y component. So right here we have E, we have an EX, and we have an EY. EX going to the right, EY going up. But now this bottom portion down here once again has the same thing. It has an EX in the same direction. Only now EY is pointing down like that. So this should already make sense to you that when we integrate over this full length of the rod to figure out the total amount of electric field at the origin, the Y components are going to cancel. There is a mirror image. If you think of this horizontal as a mirror, there is a mirror image in the opposite direction along the Y component. So all of the electric field components in the Y direction are going to cancel, and all I'm going to need to do is look at the X components of that field. Okay. Now the best thing we can do here is we can think of a small length element. Again, if you guys are really, really good with your calculus, this should come by second nature. We've talked before that you guys are going to be better at the math than I am, so please correct me if things come up. Hopefully in a video I did a good job of avoiding those sorts of things. So we're going to consider a small length element ds, a distance r away from the origin, and notice it is always a distance r away from the origin because this is a kind of circular portion of a rod. And then I need to integrate over that full distance of the rod. Let's say that that rod has some length, okay? And then we're going to use the angle to figure out the x components of those rods, okay? So our basic small length element is going to produce a small electric field element. Small length element produces a small electric field element. We know that the electric field, let's just keep it in terms of magnitude right now, is 1 over 4 pi epsilon naught times a small charge element some distance away. Small charge element dq creates a small electric field element dE. But now I've got to figure out what dq is. And dq is going to be based on something called the linear charge density ds. Okay? Now think about what the linear charge density is telling us. That is telling us that some linear charge density is based on how much charge you have and your length of the rod. Okay? So if I knew my total charge and my total length, then I have something called a charge density. Here, the small amount of charge is going to come from a small amount of length for the rod. So now I can substitute this lambda ds up here inside of dq. So I'm going to get something that looks like dE is equal to 1 over 4 pi epsilon naught lambda ds over r squared. Now ds refers to the length of this guy right here. So that's actually the arc length of this circle. That's going to be the arc length of the circle. So we have to relate the radius, the angle, and the arc length. If we go back a little bit, remember some algebra that you probably forgot by now. We know that some arc length, ds in this case, is going to be equal to r times d theta. You guys probably remember this as s is equal to r theta, but since I have a small arc length, that sounds terrible, is equal to the radius times d theta. And notice that I'm using d theta here because I'm going to integrate over the angle. And the reason I'm going to integrate over the angle is because in a second here, this is still just the magnitude of the small amount of electric field. I need the x component of that small element. So there's going to be a cosine theta thrown inside here. If we look down here with this angle right here, I'm going to need the cosine of theta in a second. I've already got a d theta here over the integral, so that's going to make the integral very, very nice. Okay? Trust me, we're going to go ahead and figure that out. Okay, so now with the next substitution of r d theta, now I have that dE is equal to 1 over 4 pi epsilon naught. Lambda stays inside, r d theta over r squared. Okay? Now I need the x component of that small electric field. The y component's all canceled out. That's the argument that we made right at the very start. So to get the x component, I have to have 1 over 4 pi epsilon naught lambda r d theta over r squared. Only now I have to multiply it by the cosine of theta. Okay? And yes, those r's are going to cancel out, so I'm only going to have one r left over in the denominator. And then I can collect my d theta and my cosine theta, and we come up here and we have dEx is equal to 1 over 4 pi epsilon naught. In this case now we're going to have lambda over r, and we're going to have the cosine of theta d theta. Now again, small amount of electric field. So I have to integrate in order to get the full amount. The limits of my integration, since it's given in terms of a small angle component, the limits of my integration are going to be 60 as my upper limit and negative 60 as my lower limit. So we're going to integrate here. So E in the x direction is equal to the integral of dEx, which is equal to the integral from negative 60 to 60, 1 over 4 pi epsilon naught lambda over r cosine theta d theta. Now notice that the 1 over 4 pi epsilon naught and the lambda over r are all constants, so the only integration that I'm doing is the cosine of theta d theta. Cosine theta goes to negative sine theta. Okay? That's going to go to negative sine theta, so we're going to get that that electric field in the x direction is equal to lambda over 4 pi epsilon naught r, the sine of theta. And that's going to be evaluated from negative 60 to 60. So something like that. Put those limits of integration in, and we get that the electric field in the x direction is 2 lambda over 4 pi epsilon naught r sine of 60. Sine of 60 is the same thing as the sine of negative 60, so that's where the 2 comes from. Sine of 60, yes, you could put that in right now, but we're not so concerned about that. That is the electric field in the x direction due to this arc length of charge that had wonderful symmetry with our horizontal axis. Without that nice symmetry right there, we're screwed on this problem. So sometimes it's going to pay to actually move your coordinate system in such a way that you create that very nice symmetry to try to eliminate some things. We're actually going to see that in the next problem. The symmetry is going to come up again. To review, we have this guy right here. We know that we go from 60 down here above the axis and 60 below the axis. If we draw the picture of what the electric field looks like, those y components are going to cancel, so all I need are the x components. In order to get those x components, I'm going to take a small amount of charge to figure out the small electric field element. That small amount of charge comes from something called the linear charge density, which also comes from the amount of charge divided by the length in question. That allows me to get a nice integral in terms of the length, but now I have to integrate over this arc length, which isn't very nice. But since r is fixed, and I can figure out the angle theta because that's been given, I can transform the arc length into a nice r d theta, and then that makes my integration fairly straightforward, the upper limit being 60 degrees, the lower limit being negative 60 degrees. Okay? This is actually done in your book. I will put the page numbers into the email when you get these videos. Please take a long look through these. I did not spend enough time in high school when I was trying to go over these, and it made it really, really tough on me. So go through, take your time. Also keep in mind that they like to say, with a little bit of math, you can get the right answer, and that little bit of math is probably everything that we did right here. So don't skip over the math, actually figure out what's going on.